Welcome again to the workshop. Hopefully you will hear the bees buzzing. So as Natalia said, this is the third international workshop on the bees algorithm and its applications. The first two workshops were very, very successful. And this one is likely to be even more successful because of all the things we have planned for you. So in terms of registrations, we have had over 190 registrations from 21 countries. So it's a truly international event. In terms of presentations, we have 20 presentations from 53 authors and from 10 countries. 23 universities are involved altogether. Now, this is not including the two keynote presentations, which are the highlight of today. So the program for today is as follows. After this opening, we'll start with our keynote speeches. The first one is going to be given by Professor Xin-she, and the second one by Dr. Laili, Yuanjun Laili. And then we have a little break, whether you have coffee or tea or you just have a break. We'll have a short break, and then we go on to the parallel sessions, the main part of the workshop. So we have two parallel sessions going, and then after the first set of parallel sessions, we'll have our lunch break, and then parallel sessions again, and then we'll close. So I hope you will enjoy the event. We start then with the first keynote by Professor Xin-she. He doesn't need to be introduced really, because everybody knows him. He's so prolific in his publications. He's invented so many algorithms, the cuckoo algorithm, the bat algorithm, the firefly algorithm. You know, he's very, very well known. And I'm extremely pleased to introduce Professor Yang and his presentation. He's going to talk about nature-inspired algorithms, some insights and open problems. So Professor Yang graduated from Oxford University. He worked at Cambridge University, and then now he's at the Middlesex University of London. He is a fellow of the Institute of Mathematics and its Applications. I was going to say Institute of the Bees algorithm and its applications. We don't have such an institute yet. But now, Professor Yang, I leave the microphone to you. Thank you very much.
Thank you very much.
So I stop sharing.
Thank you. Let me share my screen. Okay. Thank you very much, Professor Pham, for your introduction. Hello, everyone. And also, thanks, Natalia, for helping organizing this. Maybe I should say good morning, good afternoon, or whenever you are. It's really good to see you, even if it's online. My talk would be about some kind of informal insights or some of the open problem. Let me see. Yeah, okay. Right. When we talk about optimization or nature-inspired computation or nowadays machine learning, all these things are in a way related to in some way in terms of mathematical formulation. Just in case you work in different area, but you can always think about these insights or open problem from a different perspective, because in the end, we need to understand many things in terms of nature-inspired and optimization and also machine learning. So let me start with the summary of optimization in general, because it's related to many areas, because we have to maximize something like machine efficiency, energy efficiency, accuracy, but at the same time, we have to minimize the costs and wastage and environmental impact. But all these things can be somehow, if we do this properly, can formulate as a set of objective function, sometimes more than one, and subject to multiple constraints. Of course, I work with a lot of engineers and also people from different area. But some of the example I hear say like the design of car brake, gearbox, and the structure, building structures. But when we think about optimization in general, we should consider maybe at least the 4 different components. The first thing is we should decide what algorithm we should use to solve the problem under consideration. But at the same time, we have to consider the constraint, because constraint handling is also an important part of the optimization problem solving. But the most important part in many of the applications like aerospace engineering and protein design or many others, the most important part is the evaluation objective, because that's the most computational expensive part. But once you've done all these 3, but then you have to make sense of the solution or make sense of the option presented by the algorithms. But the question is, all these part, each part is very difficult in a way. For example, the choice of algorithm, nowadays we have so many different algorithms, which one should you choose? Let's start with the very basic. So when we talk about algorithm, we mean we have a procedure, we have a solution, even randomly guessed, or some based on our knowledge, we have a solution. Maybe it's not easy to find the first solution, but if not, we just randomly generated a set of solution vectors. Then we have to compare the different solutions. Then we decide how to improve them. So this is in general the procedure. But of course, the well-known one is the Newton-Raphson based, because it uses gradient and the second derivative. The question is, probably people ask is, why we need new algorithms? What's wrong with the traditional algorithm? The short answer is, there's nothing wrong with the traditional algorithm. The only problem, the traditional algorithm, most of them are local search, which means the final solution may depend on the starting point, with the exception of the convex optimization, because convex optimization means the solution you find, if it's optimal, that's the only optimal we can find. There are so many algorithms from 1960, maybe nowadays more than 250 algorithms, or including their variants. But a lot of things developed in the last 20 years, which is in a way more interested in the current context, because when we say nature-inspired algorithm or evolution computing or nature-inspired computing in general, or sometimes we call the meta-heuristics, it's this class of algorithm. The first important part type of this algorithm is the Bayes algorithm. The whole workshop here, this wonderful workshop, is about Bayes algorithm. So initially, I wish to say something, but I think it's better to skip this part because you already know most of this working mechanism of the Bayes algorithm, and from the later presentation, I have seen from the title and abstract, you have a diverse application and different perspective to analyze and use this algorithm. So probably I will skip this part. So I will move on to something slightly more different in a way. We try to highlight a few insights. When we talk about particle swarm optimization, or nowadays we talk about swarm intelligence, we tend to think about things in general, but actually we have to somehow map the idea into some equations. For example, the particle swarm optimization, we have two equations. One is the update of the velocity. The other equation is the update of the position. But the position is a position vector in the n-dimensional hyperspace, which can be considered as a vector or solution vector to the problem or any optimization problem we are trying to solve. But if you look at the two equations, all the terms are linear. So this is a linear system. So from a dynamical system point of view, this is a linear system. The behavior is controlled by the eigenvalue of the dynamical system matrix. But the question is, what we can say about such a system? Actually, Clark and Kennedy did analyze this in 2002. They conclude there is a bifurcation in terms of behavior, which is alpha plus beta. When it's 4, it's a critical point. If it's less than 4, and the behavior will be different from the setting of alpha plus beta greater than 4. So this is one general insight, means the parameter of any algorithm may lead to some kind of a bifurcation if the system behavior is in the right context. Otherwise, the parameter setting can control or influence the behavior of the algorithm. The other algorithm I mentioned is here is it's the Firefly algorithm. The reason is the original intention is to try to improve the behavior, some of the what called the premature behavior in the PSO, because the PSO is efficient, but under some parameter setting, it can behave in a way it's got stuck somewhere. The solution is not optimal, but it's not improving quickly, or the improvement is very slow. This is called the premature convergence. There are many variants try to improve this. One of the ideas is to introduce some kind of inertial weighting, which is somehow to a degree, it could be very useful. But the other problem is related to the energy, which is the velocity, because the kinetic energy is half mv squared. The higher velocity means higher kinetic energy. That means that the system will becomes more energetic or less stable, or the convergence rate is slow. One of the motivation from the nature and try to get inspiration from nature is to design this Firefly algorithm. Basically, we get rid of the velocity. So for Firefly, we only have the solution vector updated by the closeness or attractiveness of the two solutions. Suppose you have a two solution xi, xj, then their similarity and the dissimilarity will affect how you update the solution. But this equation is based on the light decay behavior of the Firefly in the tropical night sky. So this is only one equation, but if I code it into say MATLAB or any programming language, then we can run the simulation. So suppose we have this Ackley function. This display is 2-dimensional, but the idea applied to 200 dimension or even more, as long as we have enough computer power. So one of the parameter used is gamma, which control the scale. Suppose I run this simulation briefly, use gamma equals 2. Then we have a 40 Firefly. It is the whole swarm around. It may subdivide into, in this case, initially 3 swarms, then 2. Now you have this few swarm here. Then one swarm did converge into this global optimal solution. But suppose I tune this parameter slightly, then make the different, in this case, smaller, then the convergence is much faster. So the idea here is this, based on whatever the algorithm you use, they typically have some algorithm-dependent parameter. We should tune the parameter in such a way, make the algorithm efficient or as efficient as possible. The other thing is, when you look at the path of the fireflies, then you have this tree-like structure or fractal-like structure. But if you look at the nature, the paths of the firefly are sparse. So we try to basically simulate if we can use a sparse search to figure out an efficient way to search the search space or parameter space. Right. Because of the time constraint, I will not introduce other algorithm. There are many algorithms, probably more than 150 algorithms nowadays. Now, I did a little bit of reading a few weeks ago. I think my impression is there are probably more than 250 or maybe at least 200 algorithm variants. And the short question is, are they in a way useful, or do they really work? Actually, this is the important area. Even from this workshop, you see they do work a lot of application in different area. And all these different algorithms, they do work. There's each year, probably there are thousands of new articles published in this area. But I will probably give you 5 examples quickly. One is for the structure design. One of the objective is to minimize the material, in this case, the steel used, so that to reduce the cost. For these two type of structure design problem, like dome and tower design, BET algorithm indeed obtained very good results. The other example is the machine learning. For example, the deep belief network. There are some hyperparameter we need to tune so that it makes this kind of method works well. Then we use a BET algorithm to tune this set of deep belief network. Again, we got very good results. The other example is the image processing. For example, how do you access from the satellite image the damage by certain floods in certain region? This research group in India, they compared 14 different algorithms. They conclude Firefly algorithm gave the best results with the minimum amount of computational time. Also, in terms of the vehicle routing, it's one kind of a traveling system problem, but this is in a way asymmetric traveling system problem subject to real-time traffic. Think about the delivery, a set of a vehicle, like Amazon, they deliver the goods to the customers. In this case, this is the example in Northern Spain. They deliver the goods to medical goods and newspaper to the customer. Then they collect the old newspaper to recycle. So this, again, we use this Firefly algorithm with a discretized version then to solve this type of a problem. The results are very good. And finally, the what called swarm robots. It's basically saying you have a vast region, you have some unknown targets, like maybe forest fire or some unknown target. You fly drone or some battery-powered robots. There's no central control. Each robot is an individual agent. The target is to find, the objective is to find the unknown targets, but you have to minimize the time to find the target, also minimize the energy consumption because it's battery powered. So we use a combination in collaboration with an Italian research group we use a combination of firefly algorithm with the anti-colony optimization. Then the results by simulation is really good. Right. I think I have a few examples more, but I will skip them. Then I will start with another insight is how do you analyze such algorithm? Because the algorithm nowadays they are diverse, but how do we in a way understand them from mathematical point of view, statistical point of view, or even purely by simulation? Then the question is, can we analyze the exploration and exploitation abilities, or the different, say, the stability of the algorithm and the conversion of the algorithm? But in this area, it's very messy in a way. What I mean messy is some people try a little bit of this, some people try a little bit of that, but there's no unique insight we can understand what happens in terms of the algorithm. But the good things, there are some progress in the last few years. Let me give you some example. One is the use the dynamical systems theory to analyze the beta algorithm. I didn't introduce the beta algorithm, but I can write this algorithm as 3 equations. So the updated velocity, tuned by frequency, and updated the solution vector with this increment. Then I generalize this by introducing more parameters so that I can see what happens. I change the strengths of a different term. Then I can do the analysis, use dynamical systems theory. Then I can conclude the parameter should be in some triangular region. If the parameters are within this triangular region, the algorithm is efficient and stable. If it's outside, it becomes maybe unstable, or maybe it can get stuck somewhere. But it's in the yellow region or boundary, it seems still works. So this highlights another important issue is parameter setting are very important for any algorithm. Right, let's come back to this. People talk about a lot about this exploration and exploitation. Exploration means you search different area as much as possible. Exploitation means you use the information like the gradient or landscape or objective value, try to figure out what happened, how to decide the search steps. If you combine all the different algorithms like the B algorithm, anti-colony, the simultaneous particle swarm, firefly, you get this type of compromise. It between these 2 extremes of this behavior. But people think, what happened here? So this is what called the free lunch. Unfortunately, they do prove the mathematically in 1997. Free lunch do not exist in a way. Free lunch is either what they mean is it's basically there's no single algorithm which can claim to be the best to solve all problems. There's no such thing. Right. Let me finalize with this 5 open problem. When you think about your application, when you think about the algorithm you are using, maybe think about the 5 questions. One is, how do you build a unified theoretical framework to analyze the algorithm, like B algorithm or Firefly algorithm? How do you analyze its convergence, the rate of convergence, or stability? So this is still a very important area, but not much work done. So this is one. The other one is the parameter tuning. I mentioned maybe a few times, say, the parameter setting are important. But the question, how do you tune them effectively? People try to use either the empirical scanning, just say, I try every possibility. Sometimes it's not possible. Then they say they read the literature, they use their results, then they try to perturb the parameter to see whether it works. But the one question is this: if you tune the algorithm correctly for a certain set of a problem, but if you have a new problem, a new set of problem, will the parameter in somehow you tuned be still useful to do the somehow say it's still the best parameter setting? This is still an open question. The other one is the benchmarking. When you read a lot of the publications, you realize there are a set of functions that people use. But my impression is this: all these function tests are not useful because the real world application may have nothing to do with the smooth functions. So the question, probably, please think about is what are the useful benchmarks, like probably ideally real world design problem. The other things related to this is the performance metric. People claim they have, suppose they have a five algorithms, 10 questions. Then they try all these different combination. Then they say algorithm B is the best among the A, B, C, D, E. Now the question we ask is what performance measure they use. They use maybe accuracy, the minimum number of computation time. But the question is, are they fair? So this is the question we should consider. It's like you compare a marathon runner with a high jumper. What's the fair measure to compare these two different category of athletes? So this will be another question. The final question is scaling up, because all the publication in terms of the different problem, the problem they solve is tend to be in a way small scale. Maybe a few hundred design parameter, that's good enough. Most time it's maybe under 20 design parameters. But the real world problem are a large scale. The question is, how do you scale them up? Do you use a simply more computational capacity, or do you redesign the algorithm? And one of the related problems is to understand that people talk about a lot swarm intelligence. What they mean, swarm intelligence? What is the condition to somehow you can figure out this swarm is intelligent under what condition? So it's the rise of the true swarm intelligence. And finally, I leave this slide with some reference under my email. Thank you.
Now we go to our second presentation, second keynote presentation by Dr. Yuanjun Laili. So let me just say that Dr. Laili is very well known in the Bayes algorithm community. She is the author of a very interesting algorithm, and in fact several versions of the Bayes algorithm. But the one that I know best is the one on which she calls super fast Bayes algorithm, and that one has 0 parameter. So you don't have to set any parameters, and you can use her algorithm. Now, she's an associate professor in the School of Automation Science and Electrical Engineering at Beihang University in Beijing. Her research interests include intelligent optimization theory and algorithms, modeling and simulation of complex systems, robotic disassembly for remanufacturing, and that is our common work, and online incremental learning. She has managed 2 national key research development programs, 3 national natural science foundation projects of China, and participated in 2 national high-tech programs. I will stop here so that Dr. Laili can present her work to us on configurable Bayes optimization for disassembly sequence planning in remanufacturing. Dr. Laili, over to you, please.
Thank you very much. Thanks very much for Professor Pham's invitation, and thanks very much for Natalia's kind help in previously. And I'm very happy to be here to share the topic configurable optimization of disassembly planning for remanufacturing. As we know, remanufacturing is seen as a promising way to create values from end-of-life products. And robotic disassembly is a key to remanufacturing. It retrieves reusable subassemblies and components and the materials by robots automatically. Unlike new product assembly, disassembly of end-of-life products can be affected by significant uncertainties caused by structural degrading, such as wear out, corrosion, or even missing. And this can create many unforeseen end-of-life conditions. These uncertainties can cause frequent changes to disassembly plans and therefore reduce the efficiency. And here are some common products for disassembly. We know each of them contain about 10 to 30 components and requires about 200 to 2,000 simple operations to implement full disassembly. And the most commonly used operations are unscrewing, separation, and pulling. To enable automatic disassembly, we need a simple description on the components of a product to be disassembled. And usually we can use 4 typical ways to represent a product to be disassembled. They are interference matrix and/or graph disassembly, precedence graph, and the liaison graph. For automatic robotic disassembly, recognizing the interference relation between components and the available directions to disassemble these components are very important. Therefore, we choose interference matrix as the basic product representation. An interference matrix can be extracted from a CAD model, in which each element represents whether one impedes another in a specific direction. Using traditional Boolean OR operator, we can find detachable components step by step from this matrix. But when only subassemblies are detachable, OR operators cannot detect these subassemblies. However, when a component fails to be disassembled and the destructive operations is not allowed, subassembly is more likely to appear. To further detect whether detachable subassembly exists, we propose to use add operator to count the number of obstacles for each component from each direction. If a group of components form an obstruction loop without external interference in a specific direction, they can be seen as a subassembly. Here's the framework of our double point detection strategy. The add operator is introduced to form the candidate's head element and then minimize the detection steps. Each unlabeled candidate leads to a detection process. By moving the start point and the end point of a detection list, the minimum of the maximum interference loop can be found as a subassembly. For the product shown before, we can find C1, C2, and C3 with the minimum sum to be the candidates. After that, F3, which holds the shortest direction list, is firstly selected to push into a new list, P, with direction 2. And we could find its obstacle C2, then the obstacle C4, and the C4 is blocked by F4 and back blocked by the second element in the detection list, that is C2. Therefore, the start point is updated to be 2. As the obstacle of F4 is C4, and we can find C2, C4, and F4 from a subassembly. with the same process, we can find C1, F3, and C3 from direction 4 as a subassembly. The interference loops can be drawn in the bottom right side in our slide, and the procedure of the double point detection includes several iterations. It incorporates both detachable components and subassemblies layer by layer. The available direction list for each element is also included. It is different with traditional sequence. It is a segmented sequence with components and their detachable directions. For example, the direction in x-axis with x plus or x minus, or subassembly like C1, C3, and C4, and their detachable directions. Current research usually takes the n components to be disassembled the sequence. In this way, they can swap any two components in a sequence. But in this way, feasibility check should be carried out to evaluate whether a new plan violates the precedence constraints according to the interference matrix or the and/or graph. In the segmented sequence, only the elements in a same segment can be swapped with each other. The segments instead are used to represent the precedence constraints. Then we take the sequence and the directions as the decision variables and the total disassembly time as the main objective, which include the basic time, the direction change time, and the tool change time. Based on the segmented sequence, we can also consider the disassembly uncertainty by introducing interference probability matrix. This matrix defines the probability that a component interferes to another. Each of its elements is in the range of 0 to 1. It is calculated by the original interference matrix and a deformation probability matrix and an estimated interference matrix. A deformation probability matrix, DPM, gives the probabilities that n components are deformed in different types. It can be calculated using statistical data of product use. An estimated interference matrix, EIM, gives the interference probability that the deformed components impedes other components. It has the same size with the original interference matrix, and it is updated during the disassembly process with historical data. Then the interference probability matrix is calculated according to the central formula in the slide. And then the interference probability matrix can be rounded by a threshold to a 0-1 matrix, just like the original interference matrix. And according to the RIM, the rounded interference matrix, a new segmented sequence can be generated using the updated rounded matrix. And suppose the failure probability of disassembly a component or a disassembly is 5. Then the expected disassembly time, the estimated economic value, and the success rate of a subassembly plan can be calculated as the objective functions. And we can also include other objectives such as disassembly pollution, the energy consumption, the total time of human assistance into the objective function with based on the segmented sequence, and our decision variables are not changed. They are still the sequence and the direction. Based on the generation of segmented sequence, our target is to find feasible solution for a robot to disassemble an end-of-life product. We mainly inspired by the BEAS algorithm, which involves both global search and local search, and balance the exploration and exploitation through the evolution. The original Bayes algorithm uses two-layer iteration to explore potential local area and exploit the best ones with neighbor size shrinking strategy. It is proved to be very efficient in both disassembly sequence planning and line balancing, but a little bit time consuming for faster planning. And to adapt it for faster planning, we propose a ternary Bayes algorithm, which holds 3 different operators and 3 individuals. The local search is to find greedily the best left or right neighbor for randomly selected variable's position and do the swap. Waggle dance is introduced to sort the individuals and assign them accordingly. And the site abandonment is to give up some exploited area to avoid the local convergence. And our experiments are taken on 3 cases. One is shown before, and the other 2 are shown in the left side of our slide. And we generated 9 cases with different failure components. The double point detection strategy is able to find all detachable components and subassemblies within 1 millisecond. And in the planning algorithm test, we take 2 greedy search algorithms and 2 genetic algorithms. And we test ternary Bayes algorithms with 2, 3, 5, and 10 individuals termed TBA-N, TBA2, TBA3, TBA5, or TBA10. And from the box plot, we can see that TBAs perform the best with stable small variations. From the evolutionary trends of these algorithms, we can also find that TBAs can always find better solutions than the others. The statistical results of pairwise Wilson test at a significant level of 0.05 shows that TBA3 performs better. And here's the time results of these algorithms. Here's some short conclusion. And as the products to be disassembled are increasing and the different products has different end of life conditions, robotic disassembly can be executed with multiple manipulators and human beings distributedly and collaboratively, just like a more complex job shop scheduling problem. In this case, there will be a lot of segmented sequences representing products of different end-of-life states to be disassembled. The variables of disassembly planning can increase exponentially. Based on the previous work, we extend the ternary Bayes algorithm to a new Bayes configurable framework to solve the disassembly sequence planning problem with large scale. The main frame is shown in this slide. After initialization and the waggle down sorting for a group of solutions, we incorporate multiple local search operators and global search operators. For example, we can apply different differential evolution operators, mutation operators, and full range operators as the candidate operators, and applied bit climbing, box complex, and power operators as the local search operator. And we can also apply a hyperheuristic to configure the global search and the local search for each solution automatically, and therefore generate different optimization algorithms. If better solution is found, a neighbor shrinking strategy and site abandonment is applied to narrow the search space, and the population are updated and give back to the waggle dance sorting and the next generation evolution. From the local search side, we classify the operators to short-term ones and long-term ones. Short-term ones means to do local search with less local iterations in a small scope. The long-term vice versa, and we define a rule to select short and long-term according to the search pace. From the global search side, we try to encoding the operators in a unified way and made random choice. And the experimental results on some benchmarks show that the new Bayes configurable framework with hybrid local search and global search operators perform much better with less searching time and less evaluation costs. These results then inspired us to establish a coding-based configurable evolutionary operator. Here is its presentation. Suppose the population of the G's generation is Xig, and we will first do random shuffle to rearrange the population as Xg apostrophe. Then we let X0G apostrophe as the best individual we have found ever. Then we have n+1 individuals in the population. The new individual is generated through the formula in the bottom left side of the slide. The first term, omega xag is the base. The information of omega xag is maintained according to the weight omega. Then the gradient to generate an individual from xag is determined by the second term. K is a parameter to determine the number of gradient vectors applied to update xig plus 1. And the F1 is a scaling parameter, and the HPE is a probability of applying the second gradient term. The third term is a random term, and the delta rand means a random noisy in the range of x min to x max. F2 is a scaling parameter. F2 is a scaling parameter too, and the 1 minus HPE is the probability of applying this random term. We can see that in the second term, the probability is HPE, and the third term, it is 1 minus HPE. That means each time we should use the gradient term or the random term just once, choose one to use them. Then the fourth term defines the probability that the new individual roll back to the old ith individual xig, just like the differential crossover operator. So we can use 7 parameters, PE, PC, K, omega, A, F1, and F2 to represent an operator, an open operator. Using different parameters, we can generate different evolutionary operators, and using different parameters, we can closely simulate the different classical operators, just like the rand1 operator and the update strategy of PSO and the update strategy of harmony search and the different kinds of multi-point crossover. And in this form, we can generate much more. We can generate tens of or even hundreds of operators with different parameters. In our algorithm design, we use only random strategy to generate an operator according to the coding-based operator formula, and we have introduced previously. In each generation, we generate a random operator to generate each individual. To further accelerate the evolutionary search process in solving the disassembly sequence planning problem, where various products are to be disassembled, we introduce a parallel framework. We divide the population into several subpopulations. In each generation, each subpopulation generates an evolutionary operator to update their individuals. We adopt a subpopulation to search independently for a small period. After tens of generations, each subpopulation selects a neighbor and transfers a solution to the neighbor. And if its generated operator produces better solutions in more than 2 generations, the operator itself is also transferred to the neighbor. That means the parameter of the configured operator is transferred as well. If a subpopulation receives a good operator from outside, it does not need to generate a new operator in the next generation, and it will use the good operator from its neighbor to generate the individuals of the next generation. In this way, the subpopulations can always keep a dynamic collaborative search and share good operators. And here we use a rotated neighbor learning strategy. In the rotative learning strategy, each subpopulation will select a neighbor. We define the neighbor as theta. We determine the theta rotatively as shown in the bottom equation. In this way, the propagation speed of a good operator is log n, and they will select different neighbors to propagate their solutions and their good operators. And the space complexity and time complexity are both low. With the parallelization, the time for generating high-quality solutions for more than 1,000 disassembly sequence patches with the same quality is only 9 seconds. We use only random hyperheuristic to configure coding-based operators, and we use the simplest grouping way and the parallelization topology to solve this problem. So we can conclude that there's still plenty of space for us to design a hyperheuristic to generate more efficient base optimization framework to solve this problem automatically from the local search site or the global search site. And there is also a plenty of space for us to design grouping strategy and parallelization ways to accelerate large-scale disassembly planning process. Here, more question for us is that, can we apply AI models to generate suitable coding-based operators during the evolutionary search process, or make efficient recognition on the next components or subassembly to be disassembled, and even generate precise operation for a robot directly? This might be our next work to find these answers. Thanks for listening.